Ready, 3, 2, 1, action!
Good morning everyone. Today I would like to present our laboratory experiment titled Volumetric Analysis of Vitamin C in Fruit Juice. In this experiment, we focus on determining the concentration of vitamin C, also known as ascorbic acid, in different types of fruit juice using a titration method. This experiment is important because vitamin C is an essential nutrient for the human body, especially for boosting the immune system and maintaining healthy skin. However, the amount of vitamin C can vary depending on the type of fruit, processing methods, and storage condition. Therefore, it is important to measure and analyze its concentration accurately. Through the experiment, we apply the concept of volumetric analysis, which is quantitative analytical method used to determine the concentration of solution by reacting it with a standard solution of known concentrations. This presentation will cover the objective of the experiment, the basic theory behind titration, the methodology, result, and discussion of our findings. Before we continue, I would like to introduce my group members who have contributed to this experiment. First, myself, Anis, who is presenting this part of the introduction and overview of the experiment. I'm presenting together with Nur Shardina binti Shamsul, Fatin Norliana binti Sabu, Nur Aina Balkis binti Abu Bakar, and lastly Nur Eliani Sofia binti Basharuddin. Each member has played an important role in completing this experiment successfully, and we work together as a team to ensure accurate results and a better understanding of the experiment.
The objective of this experiment is to determine the quantitative concentration of vitamin C, which is ascorbic acid, in a given sample of fruit juice using volumetric
analysis. Now, I will briefly explain the introductions of this experiment. This experiment is based on a redox titration method where vitamin C acts as a reducing agent. In our experiment, we use a standard solution, commonly iodine solution, to react with the vitamin C present in the fruit juice. Once all the vitamin C has reacted, the excess iodine will react with the starch indicator, producing a blue-black color. This color change indicates the endpoint of the titration. By recording the volume of iodine solution used, we can calculate the concentration of vitamin C in the fruit juice sample. This experiment is significant because it helps us understand how analytical chemistry techniques are used in real life, especially in food science and quality control. In addition, it also improves our skills in handling laboratory apparatus such as burettes, pipettes, and conical flasks, as well as performing accurate measurement and calculations.
Of vitamin C content in fruit juice is primarily achieved through iodometric titration, which is a specialist analytical method based on oxidation reduction redox reaction. In this chemical system, vitamin C, chemically known as L-ascorbic acid, functions as a strong reducing agent because it readily donates electron. Conversely, the elemental iodine solution acts as an oxidizing agent that actively accepts this electron. As long as there is active vitamin C present in the fruit juice sample, any iodine added to the mixture is instantly reduced into colorless iodine ions. Because the reaction occurs in a strict predictable ratio, the total volume of iodine solution consumed directly corresponds to the exact concentration of vitamin C originally present in the sample. The chemistry of this experiment involved the conversion of ascorbic acid into dihydroascorbic acid. During this process, the ascorbic acid molecule loses 2 hydrogen atoms and 2 electrons, while the molecular iodine gains those electrons to form iodide ions, according to the equation. To visually monitor this transfer, a starch solution is introduced as an indicator. During the early stage of titration, the solution shows no color change because the added iodine is instantly consumed by the juice with vitamin C. However, the moment all ascorbic acid is completely oxidized, the very next drop of excess iodine has no remaining vitamin C to react with. This free iodine immediately binds with the starch molecules, forming a sharp, permanent blue-black complex that signals the official endpoint to the titration.
Apparatus and material that will be used in this experiment: beakers, volumetric flux 100 ml, stopper, measuring cylinders, white tires, funnel, conical flux, glass rod, pipette 25 ml and pipette filler, burette, retort stand and clamp, orange juice, starch soluble and potassium iodide, iodine crystal, and distilled water.
Add 2 grams of potassium into a beaker. Add about 30 to 40 ml distilled water and stir until dissolved. Add 1 gram of iodine crystals slowly into the potassium solution. Stir Stir until all iodine dissolves and forms a dark brown solution.
Next, transfer the solution into a 100 ml volumetric flask. Then, add distilled water until the solution reaches the 100 ml mark. Lastly, mix thoroughly.
Rinse the burette with the iodine solution and fill the burette with the iodine solution. Record the initial burette reading. Prepare 25 ml of orange juice into a clean conical flask. Add about 20 ml of distilled water into the flask.
Add 1 or 2 ml of starch solution as the indicator. Titrate the orange juice sample with iodine solution from the burette while swirling the flask continuously. Continue adding iodine solution dropwise near the end point until a permanent blue-black color appears and remain for about 30 seconds.
Record the final burette reading and calculate the volume of iodine solution used. Repeat the titration until consistent readings are obtained. Calculate the amount of vitamin C present in orange juice sample from the titration data.
On this slide, I will explain on the result of the volumetric analysis used to determine the vitamin C content in the juice sample. The 3 titration trial were carried out, giving iodine volume of 4.8 ml, 4.8 ml, and 4.6 ml, and the rough titration value was 4.7 ml. The average volume of iodine used was calculated as 4.73 ml. The iodine solution had a molarity of 0.0394 mol, and 10 ml of juice sample was titrated. Based on the balanced chemical equation, iodine react with vitamin C in 1:1 mole ratio. Therefore, the number of mole of iodine used is equal to the number of mole of vitamin C present in the juice sample. This volume was then used to calculate the concentration and amount of vitamin C in the juice. Next, I will explain the calculation of the vitamin C content in the juice sample. First, the mole of iodine used in the titration were calculated using the formula moles equals molarity times by volume. By substituting the iodine molarity, which is 0.0349 moles per liter, and the average volume of the iodine used, which is 0.0047 liters, the moles of iodine obtained were 1.8518 times 10 to the negative 4 mole. Since the balanced chemical equation show a 1:1 moles ratio between iodine and vitamin C, the moles of vitamin C are equal to the moles of iodine used. Therefore, the moles of vitamin C are also 1.8518 times 10 to the power negative 4 mole. Next, the concentration of the vitamin C in the juice was determined by dividing the moles of vitamin C by the volume of juice used, which is 10 ml or 0.01 liters. This gave a concentration of 0.018 mol per liter. Finally, to find the amount in 100 ml, we scale it up. Vitamin C in 100 ml is equal to 32.61 divided by 10 and times by 100. So, the final answer is 326.1 mg per 100 ml. Therefore, the juice sample contained 326.1 milligram of vitamin C in every 100 ml. In conclusion, the objective of determining the vitamin C content in orange juice using iodometric titration was successfully achieved. The titration results shows that the orange juice contained 1.8518 times 10 power of negative 4 mole of vitamin C in the sample analyzed, corresponding to a concentration of 0.0185 mol per liter. The vitamin C content was calculated to be 326.1 mg per 100 ml of orange juice. These results demonstrate that iodometric titration is an effective method for quantitatively determining vitamin C content in fruit juice through a redox reaction between absorbic acid and iodine.